Hello, grade 11s. Before we get into our unit on the properties of matter, I want to take a few minutes to discuss with you how to properly do graphs in the science classroom. Well, the essence of drawing our axis and plotting our data points is the same as it is in math. There are a few idiosyncrasies in science classrooms about how graphs are going to be displayed that we need to practice. One of the first things we need to know is that science graphs are not the place where you try to save paper. In a science graph, we always want to have a good scale, especially for the measured data points. Imagine a scenario where we have all of our data points between 50 and 70. If I started my y-axis at 0, as one would expect to do, and then plotted my equal spacing for my dots from 0 up to 70, I end up with this large expanse of wasted space. All of my data is in this very small section of the graph. It would make so much more sense if we could have just folded this section of paper out of the way so that we could spread this area out and more clearly see the trends. There is a way to do this, and we call it a crunch. A crunch is a little zigzag line that says, yes, I know that this jump from 0 to 50 is not evenly spaced with the rest of them, but that there was nothing to see down there. By doing that, I can more clearly see the shape of the graphed information and understand the trend that I'm trying to depict in my graph. We only ever crunch data on a y-axis, never an x, and we do not always need to do this. It is only done when there will be a very large sort of dead space or empty space at the bottom of the graph. You would also never crunch data in the middle of a graph. It would only be between 0 and your first measured data point. The next thing that's really important is labeling and units. First off, axes need to be labeled. You have to say what it is you're measuring. Secondly, we have to have units. For example, if I'm measuring temperature, am I measuring my temperature in degrees Celsius, degrees Fahrenheit, or in kelvins? Is my time measured in minutes, seconds, years? Both labels and units are going to be for marks when you hand in graphs for me. How do you know which axis to put each label on? In math class, you may have heard terms used about the dependent and the independent variable. The dependent variable always goes on the y-axis, the one that goes up, down. The independent variable goes on the x-axis, the one that goes side, side. When I was in school, I always found these terms confusing. I prefer to think of the dependent variable being the thing you measure. What am I measuring? In the graph above, I must be measuring time. Perhaps I'm doing a lab where I'm measuring how long it takes for the water to get to certain temperatures. So every 10 degrees, I take a time reading to see how long it took to get there. I'm measuring time, so it went on the y-axis. The independent variable then would be the thing that you control. For example, in the example I just gave you, I said every 10 degrees I decided to take a time reading. So based on this graph, I controlled the temperature. That's when I decided to do a measurement. The independent variable always goes along the bottom of your graph. The dependent variable always goes up the side. This is the biggest difference between math and science graphs, and it's that in science graphs we will more often be asked to draw a line of best fit. A best fit line is a line that best fits the dots. It may not be a dot to dot. In fact, it's very rarely a dot to dot. Well, I always want to see you draw your axes using a ruler. You should never use a ruler to connect the dots. I want you to step back from your graph and go, what is the general trend that we see? In the image here, the dot to dot doesn't really explain what's going on. But this nice smooth line that best fits the dots, I'm at least hitting part of each dot, shows a gentle upward curve. I'm seeing a trend. When dots occur that don't hit the line of best fit, typically we circle them. They are important pieces of information, and some amazing science has been discovered by studying things that don't fit the trend. So it's important as a scientist to include these. But I circle it saying this one piece of information did not fit the trend and might verify extra research. We might want to look into it more. It might have been a mistake. It might be a piece of new science that we have yet to discover. This is the last and one of the most important things that I had the hardest time getting into my thick skull when I had to do graphs in university. Titles must, at the very least, be in the form of a sentence. X versus Y, time versus temp, although fine in math, is completely unacceptable in science classrooms. You must write a sentence. The only time you're ever going to have problems trying to write a sentence is if you try to find a short, sweet version. Take the time to write a sentence. Go look up science graphs. You will notice that many of them are more than just sentences. They're entire paragraphs. And they are still written with capitals and periods, and they are always underlined. As a general rule of thumb, you could write a sentence that says the effect of, enter what was on your x-axis, or your independent variable here, on your y-axis, or whatever it was you were measuring, for the system or reaction or lab that you were trying to do. Now, this general phrase may take some tweaking to suit your lab, but if you're having problems trying to come up with a starting point for a sentence, this is a good starting point that will help you write a proper title for a graph. One of the reasons we use lines of best fit and all these labeling and all this information is because we are often given graphs to find information. When we are looking for a piece of information that is in the measured section, that's called interpolating. If I was taking data points at equal amounts, and these were the data points that I had, and then I was asked to find what the value would be at this point. It's in the measured section. I could look straight up, I could look straight over, and I could take a reading at that point and say, hey, this is at that point. That is interpolating. It's within the measured section. Sometimes, though, I am asked to find a piece of information that is beyond the measured section. In order to do that, I draw a dotted line that continues in the same path. I would not, for example, all of a sudden change directions. Please don't ever do that. By taking a look at this line of best fit, in this case a straight line, I would continue as if this line were going on, and then I could take a guess about where I would be outside of the measured data points. Interpolate means to measure within the measured data points. Extrapolate means to get information from outside. Let's do one graph quickly together. Suppose a student wanted to determine how temperature affected the solubility of a salt. Solubility means how much will dissolve. So she carefully measured how many grams of the salt would dissolve in 100 ml of water at different temperatures. And these were the results she got. Clearly what we can see that she controlled was the temperatures. She decided which temperature that she was going to put in. So because of that, temperature will go along the bottom. From the description, we can see that the amount that dissolved, the solubility, was what she measured. Because that's what she measured, that goes up the side. My temperature from the measurement is being measured in degrees Celsius. My solubility is being measured in grams per 100 ml of water. So now I have labels and units. That is 2 marks on a marked graphing assignment. Now I need to come up with some kind of equal spacing in order to record these measured points. I can see my temperature goes from 0 up to 35. Always starting the corner at 0. I've decided to mark these in 5-degree increments. So this will be 5, 10, 15, 20, 25, 30, 35. Remembering that the spacing between the dots must be equal and the increment that they go up must also be equal. Taking a look at my solubility, I have solubility readings from 5 up to a maximum of 28. Remember, my corner must stay at 0. I've decided to go up by measures of 4. I could have used a different spacing, but spreading out my points equally by measures of 4 uses up most of my page. And so now I have a graph that is going to encompass the bulk of the page, and so my scale will be appropriate. So I'm going to give myself a mark for scale as well. Now let's plot our points. At 0 degrees, I should have 5 grams. So 0 degrees, 5 grams. At 5 degrees, I should have 7 grams. So at 5 degrees, 7 grams. At 10 degrees, we are at 8 grams. I've continued marking the measured data points, matching the actual temperature to the actual reading. Now, when I stand back and take a look at the general shape of these dots, I need to draw a line that best fits the shape. We see that this shape gives me a reasonably smooth upward curve. So I now have a line of best fit. There is a small section below that is not used, but it is not very big in comparison to the size of the graph, so it is acceptable. There's no need for a crunch. What I need now is a title. And a good way to help figure out the title, you could use the general pattern, but I could also take a look at the description of the lab. In the description of the lab, the point was to determine how temperature affected the solubility of a salt. So I've decided to use that as my title, how temperature affects the solubility of a salt. It is a good description that anybody could now look at that title and understand now what the shape of the graph tells you. You can very clearly see that as the temperature goes up, the solubility also goes up. I hope that this video has helped you to understand how to draw a proper graph using the 5 good points for drawing proper graphs in science. Also, I hope that you are able to both interpolate and extrapolate to find data points on a graph. Pages 6 and 7 are an assignment where you get to practice and hand in some practice questions on drawing graphed lab data, and also getting information off graphed labs. On page 6, graph the data given with the 5 good points of a lab, and then answer the questions about that graphed information. You may feel free to use the section of graph paper included, or graph it on your own paper. Before you choose your axis, please notice that the last question is going to ask you to extrapolate at 95 degrees Celsius. So make sure that you've drawn your graph big enough to allow you to do that. On page 7, I have a very badly drawn graph that was handed in to me many, many years ago. Take a look at the data and the graph and see if you can find 5 things done wrong with that graphed information.